Okay guys, in this video what we're going to do now is we're going to prove that a sub c is equal to v squared over r. And again, you don't have to prove anything on the exam. You will just have to be able to use the formula, plug in the terms that are given, and find out the term that is unknown. I am only, guys, give you the proofs because I don't believe that physics could be understood through just plugging numbers in and solving for the term that you don't know using algebra. So that's why I have a series of videos that which are explaining you guys the entire concepts of physics, each topics that we cover. So again, if you choose or opt not to listen to the explanations, up to you. You're going to have a very superficial understanding of science, of physics. But if you actually want to learn something here, I am going to deliver you guys those lectures with the explanations. Okay, so let's prove that the centripetal acceleration is directly related to the velocity squared and inversely related to the radius of the centripetal motion. All right, so the first thing I'll do is I'm going to draw now a circle that you already seen before. I'm going to do again my best artwork here as possible. I'm going to choose now the center of this circle here. I'm going to choose a point on this circumference of the circle here and one here as we've done before. And I'm going to connect now my radius to this dot, this point on the circumference. And I'm going to do the same thing here. So this is a radius, this is a radius here. Okay. So the next thing again I'm going to do is I'm going to draw a tangent the velocity here. It's going to be just coming out from this dot, and it will be 90 degrees here, 90 degrees. Just remember it, guys, because it will come up in our discussion. And here I will do the same thing. It will be a tangent line, 90 degrees to this radius here, 90 degrees. And it has to be the same magnitude as this vector, because remember, there is an acceleration here, constant acceleration, even though the magnitude of the vectors are the same, but the directions are different. Therefore, you have a change in the velocity and acceleration. Now, so I got these two vectors. So the next thing what I'm allowed to do here, is to take this vector as long as I don't change its guys, its direction and magnitude. I can do the following. I can just transfer this vector right in here. I'm going to transfer it right in here, something like this. And this will be my, first of all, v sub 0 and v at certain time. So this is now my v sub t. Okay, so my next thing what I'll do is that I'm going to have an angle here, theta, some theta angle. And I'm going to have this angle alpha here and beta angle here. And again, if you do not want to understand how to derive this, you can just, I guess, zoom out, tune out, whatever you guys want to do. But I would not suggest you to do so because this is very important to understand the derivation of the formulas in physics. Now, so I got now these two angles here from the radius to this velocity v sub t, and also now the angle between the two vectors here, v sub t and v sub 0. So now, how do I know the magnitude now of this of these angles here? And it's very important now because I need to relate now this angle here and this angle here. In a moment, I'll show you why it is important. But we definitely know that this is a 90-degree angle here. It's a perpendicular was to this line here. There was a tangent perpendicular, so it was 90 degree here. So what we did, we transferred now this vector up here without changing its direction and magnitude. And so this is a 90-degree angle here. So if this is 90-degree angle here, 90-degree angle, then the following the following is true. That means that theta angle plus alpha angle is equal to 90 degrees also. Why? Because the sums of the angle in triangle is equal to 180 degrees minus this 90 here, 90 degrees, will give you guys the 90 degrees right here, because you got the remaining two angles that are together will give you the sum of 90 degrees. So that's why the angle theta plus alpha will give you 90 degrees. All right, what else do we know? We also know that the alpha and beta here, alpha angle plus beta angle is also 90 degrees, because remember, this is a tangent, this is perpendicular to the radius. By definition, that's what we dropped here. So now, what we can do now, we can equate now these two, because they equal, these and these will equal to the same 90 degrees. We can say that theta angle plus alpha angle is equal to angle alpha plus beta. And so we can definitely eliminate the angle alpha, and we can say that theta angle is equal to the beta angle. Okay, so now we know that this one here is actually theta angle. So I just proved it using geometry, guys. Also, what I can do now, and this is what I'm going to do now, is that I'm going to take these two vectors out. And, well, first thing I'm going to do this. I'm going to connect these two. And I'm going to say that this is my now change in velocity. This is a shortcut. Remember, guys, I derived in the previous video how to get the delta V. So I had this just 100 degree flipped, okay? But now I need it this way, because for some comparison that you will see in a moment. And also what I forgot to label, this is a C, this is O, and this is P in here. This is important for me in a moment. You will see how. So now I'm going to take this triangle here, and again, we used to see it as flipped, because remember, I subtracted these two vectors, but here I just did a shortcut. Just everything here preserved. This angle will be still the same if you flip it, but I just wanted to do it for simplicity here. So let me just redraw this vector here, going downwards. There it is. And then this one is, we want to keep the same angle. This is about this way. This is now our resultant here, delta V. This is V final. This is V initial. And voila, we got here a triangle with the theta angle here, because it used to be beta, now it's theta. We proved it Y right here. And so this is one triangle. And what we can do now, we can take the sector COP now here, and we're going to juxtapose this one also. So let me do it. So this is going to be here. I'm going to take it, rotate it here. And it will look like this. Something like this. And something like this. And I'm going to connect now this sector here. So this is COP. So I just took this out here, and remember, guys, there was a theta angle right here. So now, since you don't know calculus, but in calculus, when we're dealing with the curves, what we do is that we starting making this curve going to limit of 0 here. This is going to 0. But if we bring these two sides that are equal, by the way, are very close together, and eventually getting close to 0 here, you're going to realize that we're going to create this triangle here eventually. And so I can assume this is my triangle here. And so this triangle here and this triangle here, they call like triangle, because they called isosceles triangles, because this side here is equal to this side here, and this triangle, and theta angle here. And the reason there's V initial, V final is equal, because remember, we guys had these magnitudes of the vectors equal here. It's the magnitude here of the velocity there's the same, but the angle is different, giving you a constant acceleration. So this and this equal, and that will be called a isosceles triangle. So is this one here, this and this side equal, because they're both radiuses here. And remember, the radius in the circle doesn't matter where you measure it, it's going to be the same throughout the entire circle here. And also, this is a isosceles triangle because this side and this equal. But look what they're sharing. They're sharing the same angle here. The same angle here, the apex here. Now, what that means, they are like let me just spell triangles correctly. Hold on. Triangle. See, I can spell triangle. Oh, yeah. Triangles. Okay? Now, so they are like triangles. So what can I do now to relate the two? First of all, if you remember, this was the distance that the body that is in circular motion goes through this sector here. So if you remember the velocity here, change in velocity is equal to change in distance over time, right? So in other words, a change in distance is nothing else as a change in the velocity times the t. So this here is nothing else, just v times t. Okay? So I want to relate now this side of this triangle to this side of this triangle. So I'm going to say that the change in the velocity here, let me just move it a little bit down here. Change in the velocity here, I took it from here, to any one of these velocity, we're going to put, because they're equal, doesn't matter. And in this triangle, will be related to same side of the triangle here, which we just stated was v times t here, v times t, and again, this is my v. You can use delta v times delta t. At this particular point, it doesn't really matter much. So I just use right here divided by the r, because now this is related to this. Okay? And so if we know that the acceleration, guys, acceleration is nothing else as acceleration is the v, changing the v over t, right? Okay? Now, what we can do now, we can bring now this t in here. We can now solve it by bringing down this. It's going to be delta v over t, which is nothing else as the acceleration here. I'm just rearranging this equation. So this goes down, this goes up, v times v squared over the r. And so this now will be replaced by acceleration by a, and v squared over r centripetal. And so what we did, we just proved that this a centripetal is equal to v squared over r, and that's what the original statement was in your textbook, as centripetal acceleration is equal to v squared over r. Now, one last thing, guys. Also, your textbook mentions the equation for the force. So this will be solved in a really easy way. So we know that according to the Newton's second law, F is equal to m times a, but now centripetal acceleration we also know is equal to m times v squared over r, and that will be our formula for the centripetal force. So in the next video, what we'll do, we're going to start solving problems using these two formulas. Again, you're not responsible for all of this, but I want you guys to understand how I got from how I got here, and then from here I got here. You should guys be able to do this. I'm not holding you responsible for. I just wanted to show you how to get the derivation of the centripetal acceleration.